Thank you to the organizers for giving me the opportunity to present this discussion about policy informatics to you. I'm afraid I'm going to be taking advantage of their kindness to give you a non-technical talk that's full of opinions, loosely based on evidence, mostly on my past experience. To give you some context for what I'm going to be talking about, I should tell you just a little bit about myself. My degree is in physics. Over the last 35 years, I've worked in a lot of fields, including particle theory, fluid dynamics, nonlinear dynamics and chaos, financial market prediction, natural language processing, environmental systems modeling, transportation systems modeling, and for the last 20 or so years, epidemiological modeling. So I got lots of opinions, and I'm going to share them with you now. Without further ado, here's policy informatics. And I'm going to describe it as a kind of knowledge discovery in synthetic worlds, not unlike what you do in databases, but with a very significant difference, that we use causal models. I'll describe the who, what, when, where, and why, but maybe not in that order. And I'll also talk about why we don't use the usual suspects, the way people have done this in the past. Instead, I'll talk about how we approach it with our synthetic information systems. And then I'll issue you a challenge. First of all, let me warn you that I use the word we a lot. This is not my personal pronoun. It's also not the royal we, certainly, and it's not even the editorial we. It's just the plural. These are the folks, some of the folks who've helped do all the stuff that I'm going to be talking about today over the last 5 or 10 years. Now, why is it that I choose to work in policy informatics? Well, to start with, there's this sort of collective reason, which is that all those people that I was showing pictures of on the last slide, a group like this doesn't just come together and stay together for over 25 years by itself. It needs a lot of care and feeding. By feeding, I don't mean just supplying dollars to keep the group together. Oh, of course, that's important. But also figuring out research topics that will keep a group of really curious people interested for a long time. There's also a personal reason why I do this. I really want to make a difference in the world and leave it a better place than it was when I started. And what I'm showing here is my Google Scholar report for all the work that came out of my PhD dissertation. And you'll note that it didn't have just a huge impact on the world, didn't really make a difference, although the math was fun and I was really interested in the work at the time. So I found that when you publish work in computational epidemiology, especially these days, people really want to know what you have to say. I can't guarantee that this is going to happen for everybody who works in this domain of policy informatics, but it's indicative of the kinds of impacts you can make. What on earth am I talking about with policy informatics? It's an informatics discipline, right? It's informing something, and we're informing policy making. We're informing it with evidence-based knowledge so that decisions aren't made in a vacuum. Now, building this evidence base is not easy because it requires pretty much designing, constructing a science of really messy, heterogeneous, interacting systems. To do this, we had to create a multidisciplinary team that focuses on what we call synthetic information tools for real-world problems that are defined by our stakeholders, not by us. Just as some examples, of course, we're working on the COVID-19 pandemic. We give 4 or 5 weekly briefings to various parts of state government and Department of Defense. In the past, we've worked on the West Africa Ebola outbreak. We've done senior level exercises We've worked on 2009 influenza pandemic, the planning that was done before that, and we got started in this epidemiology world with a smallpox vaccination problem. We don't work only in pandemics. We also have participated in a bunch of forecasting challenges, although that's not the same as policy informatics. Among the 30 or so case studies that we've done for DoD in the last couple decades, we've worked on power grids, analysis of the national planning scenario number 1 that I'll talk about later on. And before that, we worked with metropolitan planning offices around the country who had specific questions about how they can reduce congestion and commute times in their cities. Just to take one example of these, let's say the 2009 influenza pandemic, let me give you some idea of what goes into this nice little list that looks so tidy here. This bullet item here says evaluate antiviral med kits, vaccine deployment strategies, etc. That's part of what we did. We got a question that said, if we put together some antiviral packages and you didn't have to see a doctor in person to pick them up, what would be the outcome of that? So that's one kind of study that we did. Another way that we worked in that pandemic was to support a daily meeting that was held at Health and Human Services of several different branches of government. And in that meeting, people were asked for their opinions on topics that had been discussed in the prior day's meeting. And they were given homework assignments, that's what they called them, to analyze the consequences of various proposed policies. And these homework assignments were due the next morning's meeting. After the fact, we were told by one of the participants who was using our models to do the homework assignments that they had canvassed the country for models that could participate in a workflow like that with that kind of turnaround. And they found a total of 2. Nowadays, if you ask who's modeling COVID, for example, you can easily find 50 or 60 or maybe 70 groups out there. Pretty much anyone who knows how to integrate a set of differential equations is modeling COVID right now. So these problems, although I haven't described them all, I'll just trust me on this, they have some common features that impose constraints on the kinds of models you can build. For one thing, they're asking us to evaluate and compare options. They're not asking us to design the best possible policies. We're not policymakers. We're scientists. We're tool makers. However, if somebody asks you to evaluate 2 different policies, you want to make sure that each policy has a fighting chance. So you want to find the optimal implementation of that policy. Another feature these questions share is that they're about targeting controls. So you want to target it to demographic groups or spatiotemporally. And often the metrics of success are equity-based. Is this an equitable solution for society? Since the policies have not yet been implemented for the most part, these are all counterfactuals, hypothetical situations. They're all resource constrained because this is the real world. You can't just throw everything you can at a problem. You have to take into account political and social constraints. The problems are multi-scale. It's almost always the case that our controls operate at the levels of individual people. And yet what we want to know is what's the population level effect of that? The way you get from the individual to the population level is through a complex evolving network of interactions. And as I said before, this has to fit within the work cycle of the policymakers, the decision makers, which generally means a really short turnaround time. The upside of that, if there is an upside, is that a 90% solution, or even an 80% solution sometimes is all that's required. You don't have to outrun the bear, you just have to outrun the next best model. I want to talk about what some of these things I've highlighted in red imply about the models that we're going to build. What it takes to represent targeted controls, how you deal with analyzing counterfactual situations, and how to build a model that can address these kinds of multi-scale issues of network dynamics, and do this all within a short turnaround time. I'd like to ask you to think about the following things. There's a set of questions, all possible questions somebody out there could ask you. And let's just pretend that each of these questions has an answer, A of Q, sitting here. And then there's a set of models that you could build. And for each of those models, it'll give you an estimate for the answer to that question Q. Now let's get the quantifiers in the right place. We can think about a model that for any question you ask it, you can build a model such that the answer that the model gives is a good approximation to the right answer. This is what we've done for a long time. The problem is that you just can't do this overnight, literally overnight. It's not timely enough to make these kinds of models. So how about if we build a universal model in such a way that for any question you ask it, there's a question that's sort of like that one, and the answer that the model gives to the original question is actually the answer to the question that's sort of like it. Well, Tukey has explained that this is not very useful. An approximate answer to the right problem is worth a lot more than the exact answer to the wrong problem. So what's left? Well, one option is to build a model such that for any question you ask, my model can give you an approximate answer to the right question. That's what Tukey was asking for. And that's the one that Goldilocks is going to say is just right. So, given all these constraints, what kinds of models are useful for decision support? I'm going to be talking here about models that provide a causal explanation of the outcome, because those are the only kinds of models I know of that you can really address hypothetical counterfactual situations with. It's not always obvious when you look at the fancy charts and stuff that accompany a model, whether it's a causal model or simply a statistical correlation model that represents a bunch of data compactly. I think the statistical models are probably what people at KDD are more used to dealing with, but I'm going to argue that they're part of the solution. They're not the whole solution, but there is a huge difference. It's like asking a machine learning algorithm to learn a language with no examples of that language. It can generalize a little bit from other languages, but it's not going to work all that well. Instead, I think we should construct causal explanations of the outcomes. Now, that's not saying that there's no use for statistical models, because the things that go into that causal explanation are bound to be coming from databases of training data. How do you go about the process of working in a decision environment like this? First of all, you got to scope the problem. That's true for anything. And here are some of the things to remember about the problems that you'll be asked. The dynamics in the system aren't smooth necessarily. They can be very stochastic. The system's open to exogenous shocks. It's nonlinear. It's pretty much any scary word that you can think of to a modeler. It's what you got to deal with. The multi-criteria optimizations, all this stuff. On the left here is a little cartoon of the process of modeling counterfactuals for decision support. And the x-axis is going to be something that represents the situation, the world as it is. It's one-dimensional here, which is pretty unusual, but that's what that axis is for. And as time goes by, the situation the world is in changes. That's all that curve is meant to represent. So the second stage is to assess the situation. Where are you right now? Sometimes this is called nowcasting, because often the data that you have available to do this with are several weeks old. Remembering, though, that the observations we make of things out in the world, they're noisy, they're sometimes just wrong, the instruments have varying qualities. So the observations are like Socrates' shadows on cave walls. Models can help you at this stage even by verifying the internal consistency of the situation assessment you've made. The next stage is, if you think you know something about the dynamics of this system and you think you know what the current situation is, you can try to model what's going to happen in the future. That is, the near future. Your models not only may disagree, but they are guaranteed to disagree about what the future holds. And there's always at least one model you can do this with. And usually there's one for each person on the planet, because everybody's got a mental model. That's how we live. That's how we interact with our environment, is by forming models of what's about to happen. So everybody's got an opinion. But remember that we don't really know exactly what the situation is. So let's hypothesize that there are many different situations that are consistent with the data we've observed so far. And each one of those has a forecast associated with it. Now, you've been asked a question, which is usually in the form of, what happens if I do this? So you're going to need to model interventions in the system, not just forecasting what happens if you leave everything the way it is right now, but if you make a change to it, what will that change accomplish? Moreover, you're generally asked to compare different options. You need to take all the different situations that are consistent with your observations. You need to model the future in all those situations and the future under different controls. And then you need to rank all the outcomes. Given that ranking, there's some way that you can choose the best course of action consistent with what you know about the world as it is now and the options you've been presented with. The best course of action may not be the best in all possible worlds. It may not be the best under all criteria, but it's better than guessing. And you can't just stop there, obviously. As soon as you're done with that, you need to monitor the changes that are going on because of the decisions you've made. See if they're consistent with what you expected. Adjust your assessment of the situation if they're not, and start planning for the next decision you have to make. Given all this, you'll never know what the true situation is. You'll never know exactly what might have happened if you hadn't done what you did. And you'll never know what kind of exogenous shocks are going to be applied to the system, or what kind of internal decisions will be made in the future. So it's kind of a fool's mission to try to forecast something like the evolution of the coronavirus pandemic for many months in advance. We don't know when someone's going to decide to implement stay-at-home measures, or what the people's reaction to face mask wearing is going to be. Okay, now let's think for a second about the implications of targeted interventions on the kinds of models you build. This is a cartoon that's actually from 2008 or 9 or so, during the other pandemic, where the pointy hair boss is asking Dilbert to run a simulation of productivity if we lost half the workforce to a pandemic. Dilbert, thinking quickly and trying to forestall the inevitable demand for immediate solution, asks whether he should assume we lose the productive people or the ones who ask people to run pandemic simulations. You can't answer a question like that unless your model has two classes of people in it, the productive ones and the ones who run pandemic simulations. Fortunately, Dilbert's model is such that he can answer either of those questions almost immediately. This is what I mean by the kinds of qualifiers I was using a couple slides ago, that there's a model that will let you handle most questions that come along. And I guarantee that if you handle some of the questions, if you handle a question about targeted control, where, say, you're aiming an intervention at left-handed people, then as soon as you answer it, you'll get a question about, oh, so what would happen if instead of left-handed people, we only applied it to left-handed red-haired people? You're best off if you design that kind of thing into the model. Obviously, you can always take the model you've got and keep refining it adding more data at each point. But the best solution really is to build a model that is disaggregate to start with, and you can aggregate up however people ask you to aggregate it. I said that it was important to look at the population level effects of individuals' behavior. This is an example from the National Planning Scenario number 1, which is an improvised nuclear device exploding in downtown District of Columbia during a weekday. And we were asked to simulate what would happen if you reinstated communications, not just for emergency workers, but for everybody quickly. People had looked at this scenario for decades. They've been gaming this scenario. And it's almost always been a question of physical effects. What happens within the first microsecond after the bomb goes off? And the casualties are tremendous, the damage is enormous. And it stops there because it's such a big event. It's hard to think of any way to mitigate the damage. But there are survivors, and the actions you take in the immediate aftermath can change the probability that those survivors will make it through the event. It's worthwhile figuring out what you can do to help them. How do you answer a question like, where should emergency triage facilities be placed? Well, let's just think about this person, Bill, here. If you ask him to shelter in place, how long is he going to shelter in place? What is going to drive him out of the shelter? What's the influence of other people nearby him? Which way is he going to go when he leaves the shelter? Gee, I wonder if it might depend on whether Bill's been in contact with his family. How would communication devices change whether he's in contact with his family? How does it depend on what the rest of his family are doing? Now you put together a few million of these people and you start getting large collective behaviors, each of them in the context of what everyone else is doing. How do you know what the context for people's behavior is? How do we do this? We do it by constructing synthetic systems, virtual worlds inside the machine, whose behavior we can control down to the individual constituent. In our case, the constituents are usually people going about their daily activities. So let me explain what synthetic data is. Synthetic system is a disaggregate representation of individuals. It includes their states, it includes the interaction they have with other individuals. It's not a movie of the real system. It's not going to match snapshot by snapshot what's going on in the real system, but it provides a statistically accurate overall picture. The individuals, like I said, in our case, are people, places, and things, but they could just as easily be cells, cytokines, and organs, or any other interacting system that you care to think of. The reason it's called synthetic is that it's a synthesis of incommensurate data, which should appeal to people working in the fields of KDD. Moreover, this disaggregate representation provides a coordinate system for incorporating new information, for continuing this data fusion. And it lets you talk about the dynamics because you have individual things in interaction. So what on earth do I mean about people being a coordinate system? Here's an example from our early work. In 97, we wanted to say something about communication networks and ad hoc networks. So we wanted to know who owned a mobile device. And in 97, there were far fewer people who did own mobile telephones than there are now. So we took our synthetic population, which already had people with attributes like age, household size, household location, workplace, income. And we used those demographic variables in combination with a database of device ownership to figure out who in our synthetic population might have a device in their pocket with them. Now, I've mentioned dynamics a few times with regard to our synthetic information systems. And let me show you what I mean by this. On the left, we've got cars traveling around on a street map of Portland, and they're going particular places. So the person in the last cartoon is going to be going to the Boeing plant. They're going there for specific activities, work, home, school, etc. And that's pretty nice. You can make these little movies and you can look at traffic congestion and all kinds of stuff. More than that, you can also look at what would happen if each of those people had little radios in their pockets that could transmit in a peer-to-peer network. What would the connectivity of that network look like? And I challenge you to think of any other way to get this kind of information, to simulate it in a counterfactual situation, unless you know how people are moving around. But that's not all you can do with it. So starting from the same traffic simulator, we can understand who comes into contact with whom and how, say, an infectious disease might spread from person to person, and where the home locations of the people who get infected might be. When you're working for policymakers and decision makers, I find that if the model has a certain face validity, that's about all the questions you'll get asked regarding that model. Just, does it make sense? Does it pass the ho-ho test? However, when it comes time to justify your work to academics, they have very different standards. And the first thing that we always hear is that this model is too complicated. It's just useless because there's too many moving parts in it. I'll have to say that this is a valid criticism. The lesson we usually take from it is that you have to use Occam's razor, which in our work is generally some sort of information-based criterion for model complexity that we try to satisfy. But there's another lesson you can use here, which is that instead of just doing statistical models, fitting to a parameterized idea that we already have in our mind of what the answer is going to look like, you can use causal models based on things that you know are correct to generate, to create the outcome given the inputs. Because sometimes the complex model is exactly the right model. I found this picture at the bottom probably 20 years after the picture at the top, by the way. While we're on the topic of elephants, let me give you an example of a simple model that is useless for decision making. It's a linear model. We love linear models. There's only one parameter in a linear model, the slope. And linear models can usually be fit well to data locally. However, of course, the actual model that you build depends on where you fit it. And the model that you build can have completely different implications for the answers to questions you might be asked. For example, how do you get down from an elephant? Well, if you're at A, your model will say that you need to move to the left. If you're at B, the model will say you need to move to the right. These kinds of models don't generalize well. For example, as every 10-year-old knows, you don't get down from an elephant, you get down from ducks. So overly simple models can lead to incorrect conclusions, even when locally they're correct. This is another way of explaining the old story of the blind man and the elephant. Every blind man feels a different part of the elephant and thinks that they've encountered a completely different kind of object. The symptoms of this are that you get a bunch of experts with loud disagreements. Each one of them has their own evidence that they can cite, and they're all wrong. For a long time, I'd say people ignored this elephant in the room. They knew that the simple models weren't right, but they also knew that there was no way to collect enough data to calibrate really complex ones. But things have changed a lot in the last generation. And now we find ourselves swimming in data, not always knowing how best to use it, how to fuse it into one single coherent view. Well, this is how you do it. And we no longer have that excuse. So we have individual behaviors, somehow or other determining collective outcomes. And the way that seems to work is that there are organizational principles, like, for example, within the body, a group of cells becomes an organ. There's a difference between a liver and a stomach that you don't notice if you're just looking at the cellular level, maybe. These things emerge at different scales of organization. The things that the different organizations do feed back through a very complicated web through each other to accomplish effects that are absolutely unimaginable if you're just looking at the individuals. Now, when you just look at the population as a whole, it's not obvious which of these individual interactions is important, how they combine to form the collective, and what kinds of feedback loops there are in the system. So some of the challenges that we have in building models like this are figuring out how to bring the system that we're modeling into contact with the data that we have available. Sometimes you have the advantage of having some natural experiments. These are not controlled experiments. They're just different things happening in different parts of the system. How do you use that information to tell you something without being fooled into finding spurious correlations? How do you distinguish causation from correlation? Everyone knows that correlation is not causation. How do you tell them apart in data? How do you quantify the overall uncertainty you have about the direction the system's going in at the end? All these challenges, I think, are things that naturally come up in KDD. Others that might be a little bit beyond the scope of a workshop like this are how you control a system with limited tools. How do you control the system efficiently if there's only a few control surfaces in the system and the energy of activating those systems may be very large? And then once you've got all this done, how do you simulate extremely large systems? You have to be able to scale up to national scale, continental scale, global scale systems with your simulations. How do different features affect the model? There's some sort of a cause here. Feature 1, F1 in that square box, is going to affect the outcome of your model. Maybe it doesn't affect it directly, though. Maybe it only affects it through F2, which is something that you can gather data on. Or maybe you can only gather data on F1, but its causal influence is mediated by some other feature. On the other hand, maybe you can only gather data on F2. Doesn't tell you what F1 is, and it has a direct impact on the model as well as its indirect impact through F2. Or maybe what you can gather data on doesn't even affect the model directly. All you can do is use F2 to infer what F1 might be, and then infer what its effects on the model are, et cetera, et cetera. I'm not going to go into detail here at all. I think everyone understands what this problem is like. And I think one of the people who understands it best is Judea Pearl, who writes very clearly about this and about how to look for causal models. So here's the challenge I want to leave you with. Lots of times, it's the case that we have to fuse data in different surveys. We have to do this because isolated facts are not science. So here's an example. In the American Community Survey, you can find distributions of things like home locations as a function of income or race. Surveys conducted by Pew Research will tell you things about religion, but also by income and race. And the CDC has a rich longitudinal survey of people's behavior that's relevant to certain risk factors for all different kinds of illness and disease. So for example, you might be able to find tobacco use as a function of income and race. If you're very, very lucky, the shared fields are identical. That is, the income brackets are the same across these three. The survey instrument used to define race is the same across all three. And so if you spend your life working with databases, you may think, oh yeah, well, this is it's a shared key and we can just do a join. You can't just do a join because what you have is not records in a database. Instead, you have distributions, except that our synthetic population turns the distribution into records in a database. It disaggregates the distribution into specific records. So what we'd like to do is effectively a database join. Let me explain this in a little bit more detail. So suppose I'm given two conditional distributions, probability of A given C and the probability B given C, that are both conditioned on the same variable. For the surveys in the example on the last page, that would be something like, given the probability of religion given income from the Pew survey and the probability of tobacco use given income from the BRFSS, can I construct the joint probability of A and B given C? This is also a conditional probability. In this case, it would be the probability of religion and tobacco use given income. Just like an unconditional probability, you could make an assumption of independence for which the joint conditional distribution is just the product of the marginals. But there's no particular reason to assume conditional independence. As far as I know, the only times when we confuse data well are when either each sample response includes values for both A and B, in which case it's not really a data fusion problem at all. It's just how do you represent the joint probability distribution that's implicit in a survey, or what I've been talking about for this whole talk, when the relationships between A and B emerge dynamically from the properties C. As an example, in the case of computational epidemiology, C might be the whole collection of demographics that lets us define what a person's activities are. And it's those activities and locations that determine who comes into contact with whom in the population and who can possibly spread it to who else. So that's my challenge, is to figure out how to deal with that problem. So as I wrap up, I'd like to leave you with one thought, which is the importance of communication in this field. And this is one place where you have to do as I say and not as I do. It's often the case that policymakers and modelers just don't talk the same language. And you have to learn to understand what they're saying to you. In particular, like this example, it's not a real example, but it's the sort of thing that happens, is that the policymakers have very specific questions and they need very specific answers. And what the modelers do is say, well, let's see, I have a model that's sort of like that. I can answer a question that's a little bit like that. And all this other stuff, it's just details. It's probably not important. It is important, and you really need to answer the right question and not the wrong question. It's not all on the modeler's end either. Policymakers do need to understand a little bit better what modelers mean when they caveat an answer. When you show someone a hurricane track that has a probability of making landfall in different places and spreads out like a cone, your answer can't be, well, I don't like that. Tell me where it's going to hit. The answer has to be, if this is the best you can do, I'll work with it. One way to ensure improved communications is to embody all the modeling in a tool that you make available for the decision makers themselves to use. This kind of goes against a lot of what we're taught in academic lives, that you can't trust people who haven't studied something really thoroughly to do the right thing if you give them a powerful tool. But we find that, in fact, with the right kind of guidance, most people can learn how to use tools, especially if they've helped design the tool. Here again, you'll note that specific solutions are preferred over general solutions. People want to know what's going to happen in this health district in the next 2 weeks. They don't want to know what's going to happen in some notional population that's about the same size and might have something to do with the population of that county. That's why I call our group tool makers. Ideally, this is the kind of thing we would like to produce. So finally, since this conference may include some people who are thinking about this area as a career, let me warn you that publication can be difficult when you're answering very specific questions because they don't have widespread interest. Not everything you do is going to be something that PNAS wants to publish. Everybody who sees a model can make a better model. It's just, I don't know, it's something in our genes or something. If you show me a model, I can tell you how to improve it. And I can tell you, you should have done this, you shouldn't have done that. But if not the specific questions, The science underpinning the answers is novel, widely interesting, topical, current. It's right at the forefront of everything that's going on in a wide variety of disciplines. Now, identifying the science, pulling it out of the questions, that's the hard part, and that's what you have to do. Because you'll find that the folks who pay for the science, they don't really know what the right questions are. And the folks who pay for the answers, they don't really care so much about the science. And the thing that goes between the science and getting the answer, the system development, nobody wants to pay for that. But if you do all this right, you can put together a great team of people who enjoy working with each other. And at the end, you can look back and say, yeah, I did make this world a better place. And it's been a lot of fun. So, thank you.